Welcome back everyone to the afternoon session of the European Einstein Toolkit meeting. The final talk of the meeting before we move to the discussion session on the Einstein Toolkit will be delivered by Brian Metzger. For anyone who may be unfamiliar with his work, he's a professor of physics at Columbia University. His work explores explosive events in the universe and what they reveal about the origin of elements, particularly the heaviest ones. He will talk about from mergers to magnetars, quest for the origin of the heaviest elements. Brian, you can start. Thank you.
Thank you for the introduction. I appreciate the invitation. I'm coming sort of at the end of the conference. Also, my talk is probably a little less technical than some of the earlier talks. I continue to be very interested in neutron star mergers, but today I wanted to spend a little time to sort of broaden the horizons and discuss maybe whether there are any other sources for these heavy elements. Of course, I'll touch on mergers because they're the prototype for understanding the observational appearance or the evidence for radioactive production of radioactive elements in explosive astrophysical events. But I want to sort of move on to discuss other sources as well that might be contributing. In fact, I'm going to argue, if I have time at the end, that we have maybe a second confirmed source of these heavy elements besides mergers. And so I think, all the tools that are being developed, you wouldn't be surprised to learn that most of these involve really, intense space-time and strong electromagnetic fields and all the things you guys care about. So maybe I'll just sort of move ahead and say, one of the goals of nuclear astrophysics is to identify where the elements that make up the periodic table come from. We know that the lightest elements, hydrogen and helium, were mainly formed in the Big Bang. The intermediate mass elements were formed in stars and expelled into space when those stars die as explosions at the end of their lives. But then as you get heavier than iron, of course, the abundances of these elements become far smaller, and it gets more challenging to actually form them. Through standard thermonuclear reactions, you have prohibitive Coulomb barriers, and so the only way to really form these heavy elements is through neutron captures. And we think we have some idea where roughly half of these elements come from the slow neutron capture process, although there are still a lot of questions there. But I think one of the remaining major challenges here is where the rapid neutron capture process happens. And this, of course, accounts for many of the precious metals and the transuranic elements and these explosions. And I think it's a profound question, if you imagine that these abundances of gold or uranium or what have you were different on Earth, the sort of way that our society developed might have been very different. So I think it's a profound question to understand where these elements come from. And this, of course, is a challenge going back to the Middle Ages, alchemy. How do you take a fairly easy to produce nucleus like iron, again, as I said, through standard thermonuclear reactions, and produce something much heavier like gold? Well, the way to do this was identified in the 1950s. You just take an iron nucleus or a seed nucleus in the iron group, and you bombard it at a very high rate with neutrons. And in this way, you create a much heavier radioactive isotope, which can eventually decay into gold. And of course, the neutron doesn't have to worry about the Coulomb barrier. Of course, that sounds good, but then, where do you get this enormous flux of neutrons? Neutrons are unstable. They decay into protons in a vacuum in 10 minutes. So where do we get this sort of transient, huge flux of neutrons in the universe is really the question regarding where the R process occurs. And an obvious place to go looking for neutrons are neutron stars, and an obvious way to get them out is to slam them together or have them merge. And we're all aware that we had this beautiful opportunity now 7 years ago or so with LIGO's first sort of absolutely certain that it's a neutron star merger event, 17817. I think one of the interesting aspects of this event was that the total mass of the binary was actually remarkably close to those in our own galaxy, which were sort of used to motivate LIGO in the first place. And so even though this event happened in a very distant galaxy, what it produced in terms of its nucleosynthesis, it might be a doppelganger for some of the mergers that are happening regularly in our own Milky Way. And so if we can understand this event, we might learn something about production in our own galaxy from neutron star mergers in the past. And of course, we had this amazing kilonova that was seen, this fading flare of light, unlike that ever seen before. And, we see supernova all the time. There were a lot of people worried before LIGO that we would have too many unrelated transients in the gravitational wave error region, we'd never be able to identify the unique one. But it turned out that this kilonova properties were very distinct from that of other supernova, for example. And the basic idea is you're creating all these heavy elements and ejecting them into space, and they're radioactive, so they cause the expanding material to stay hot and to glow, and you can observe this for several days or weeks after the event. And we had this beautiful light curve for this one event from the ultraviolet through the infrared. And all I want to say really about the kilonova here is that, by studying how bright these are, we learn something about the total radioactive power that's powering them, and that tells us something about how much radioactive mass there is. And then by studying the colors and timescales, how long the photons are trapped in this expanding gas, we learn something about the opacity sources, and opacity is intimately related to the composition of the material. And there have been quite detailed models of kilonova that have been conducted over the past, again, 7 or 8 years. But I think broadly, I still believe there's sort of evidence for at least a few different components of ejecta in this event. Certainly, there was sort of a unique early UV aspect of fading part to it, and a later, more persistent infrared aspect. And so there seemed to be some evidence. So if something's evolving fast and is blue, our belief is it has fairly low optical UV opacities, and that's what you expect for lighter R process elements. On the other hand, if you have these higher opacities that trap the radiation longer and leak outs in the infrared, then you have some evidence that you might have some of these heavier lanthanide or actinide elements. And we may have seen both in this event. And bolometrically, the sort of decay was roughly following what we expect for radioactivity. And by modeling this in detail, you can infer that a few hundredths of a solar mass were ejected at a range of velocities. So I think that's all new to you, or not new to you. You're probably all very familiar with that. Of course, there are different types of counterparts from these mergers, which have been informed by simulations. People on this call have a major role in predicting all of these things. The idea is when the neutron stars merge, you create this, usually the object collapses to a black hole with a accretion disk around it. The accretion disk accretes onto the black hole within a second or so, and the idea was for a long time that this powers the burst of gamma rays. If we're looking down the axis of the jet, we see a bright gamma ray burst. If we're off axis, we see something dimmer. You eventually see the jet running into the interstellar medium, and then you have all this sort of mildly relativistic ejecta from the disk winds and the tidal material, which is what powers the kilonova, and itself may interact eventually with the interstellar medium and produce what we call the kilonova afterglow. We've not definitively seen that yet. We may have hints of it in 170817, but for this particular event, we were viewing the event a little bit off axis, and so we did actually get to see a weak gamma ray burst. There's some contention as to exactly what produced that, and we did get to see an off-axis afterglow. I think, one of the main, in addition to the tidal ejecta, one of the main sources of ejecta in these events are the outflows that occur from the accretion disk that's formed after the event. And it's impressive to me that you have such incredible conditions in these disks, temperatures of billions of degrees, densities, 11 or 12 orders of magnitude higher than the sun. And these high temperatures enable the disk to cool efficiently through these Urca reactions. And that's important. In the midplane of the disk, you have turbulent heating, and it can be offset by these reactions. But in the upper layers of the disk, you have heating, where the disk is cooler, and these reactions are slower, and that heating basically goes into driving a wind, which you can call magnetically driven, but it may not be an ordered magnetic field. It could just be dissipating turbulence. And so that, and the combination also of alpha particle formation when these free neutrons and protons recombine as the disk cools, can eject a sizable fraction of the disk mass. And so for a typical merger that might produce a tenth of a solar mass torus, you could easily get a few hundredths of a solar mass of ejecta. And this, I think, is a natural explanation for at least some, if not most, of the ejecta we saw from 170817. So as this matter expands into space, you, of course, have to very carefully follow the weak interactions in the disk, both in the disk where electron-positron pair capture reactions are important, and as the matter is flowing out, where you also get irradiation from the neutrinos. And I'm sure you've discussed the important transport effects and oscillations and everything. So very quickly, within a few milliseconds of this matter is expanding out of the midplane, it freezes out. It's kind of like a neutron-rich version of the Big Bang. You get a freeze out of the weak interactions. The free neutrons and protons recombine into alpha particles pretty quickly. Those alpha particles then recombine into heavier seed nuclei. And then the key point is if the electron fraction is low enough, then even after you form these seed nuclei, you have a lot of free neutrons left over, which can then capture onto them and potentially do form an R process. And this is all happening within, seconds after the matter is expelled from the event. And it's pretty difficult to not get something like this happening in the ejecta from these events that are freezing out of, usually hot enough that you're freezing out of nuclear statistical equilibrium. And so, if you'd run these simulations and you follow the different sources of ejecta, the tidal ejecta, the disk wind ejecta, maybe there's a magnetar wind I didn't talk about that before the remnant collapses into a black hole, it might power its own sort of wind. You can then, run these through a nuclear reaction network and compare to, either solar system abundances or the abundances on individual metal poor stars in our galactic halo, and you can claim victory. Okay, looks like what we see, roughly. And of course, this was from our paper with Dan Siegel on the some of the first MHD simulations of these post-merger disks. But I think it's difficult to sort of forward model this process. I mean, I think it's clear that the mergers are one of the unique sources that can produce very low Y ejecta that can get us up to the second and third R process peaks. And we can also ask the basic question, which is whether they produce enough of these elements to explain the abundances on the sun, on the Earth. And here what you do is you add up all the R process in the galaxy, you divide by the age of the galaxy, and you say, okay, I need roughly 10 to the minus 6 solar masses per year, averaged over the period of time before the sun formed. We now have a rate from LIGO, which appears to keep going down as they seem to not detect as many mergers as we hoped. So you can translate that into a per Milky Way rate. And again, there's a lot of uncertainties in this, but if you do that, you see that each merger would need to produce of order maybe a hundredth of a solar mass to a tenth of a solar mass to explain, these abundances in totality. And we did have a few hundredths of a solar mass from 170817. So maybe that tells us I think it tells us these are important sources. Whether they're the only source of these heavy elements is, I think, still open for debate. I doubt they're the only source, but whether they're 99% or 10%, I still think that's open for debate. I should say that, gravitational wave triggers are not the only way to detect these kilonova. We see gamma ray bursts, short gamma ray bursts, which likely come from neutron star mergers in most cases, all the time. And if we wait for the afterglow of the gamma ray burst to fade, we can often see a sort of a kilonova emission peeking its head out above the afterglow. And so although the data is far rattier than for 17817, you can perform these types of kilonova analysis and sort of estimate how much ejecta was produced in these short GRB mergers. And Jillian Ristitijad recently did a compilation analysis of these. And this was just sort of the punchline. There's many results in her paper, but the punchline for sort of the variation in the ejecta mass for these, half dozen or so GRB kilonova shows that there is, sizable variation. Not all mergers seem to be clones of 170817. There does seem to be lower ejecta mass cases, higher ejecta mass cases, and this is not surprising per se. We should have different mass ratios of the binary, which give rise to more or less tidal ejecta, for example. We could have lower mass binaries that produce longer-lived post-merger remnants that take longer to collapse to black holes, or even live for substantially longer, and that could sizably impact the amount of ejecta and its electron fraction, for example. And then, of course, we also could have black hole neutron star binaries in this population. So I think the GRBs are an interesting, they've been picking up the slack as we've been waiting for LIGO to come through with another kilonova, but these are much more challenging to observe. I will say that I think, the one thing that gives you some pause with the mergers is just that I think there's fairly abundant evidence in our own galaxy that there's some source of prompt R process production, something that quickly follows star formation in the earliest phases of our galaxy. And there's a few examples or a few pieces of evidence in support of this. We see these ultra faint dwarf galaxies like Reticulum 2, tiny little dwarf galaxies that most of which have very little R process in them, and then a small fraction are highly polluted by these elements. And these galaxies underwent star formation very promptly early in the history of forming our galaxy, even before our galaxy formed. And they have tiny escape speeds, and so if you form a neutron star binary in this galaxy to keep it in the galaxy, it has to have a very small neutron star kicks. And there are clearly binaries in our galaxy where the neutron stars did get small kicks. This is something that Svi and Paz Beniamini have pointed out repeatedly. But I still think you need it to be, small kicks, prompt. It's not that mergers can't do it, but it would be easy to believe a supernova could do this, or something related directly to star formation. And you also see, if you look at europium over iron as a function of metallicity in the galaxy, so this is sort of a proxy for cosmic time, there's evidence that this ratio is higher in the past, which tells us that most of the europium was formed before the iron, and the iron mostly comes from type 1a supernova. So again, if you have a fraction of mergers that are prompt, a high fraction, you can explain this, but it may also be evidence that there's some other sources. I'm not going to come down firmly on that. I'm just saying it's a motivation that we should keep our minds open. And so this sort of opens up the question of what are all the possible astrophysical sites for the R process that have been discussed over the years. Of course, we now have mergers, which are a confirmed source. That's great. Ordinary proto-neutron star winds. I think the sort of jury that's come out is that it's very difficult to make those work. You need very high entropies in the winds, and you need a low electron fraction, which we don't know exactly what the electron fraction of those winds are. I wouldn't say it's impossible. There is some interesting recent work by Tejas Prasanna and at the Ohio State Group, as well as my own former student Dhruv Desai, on the impacts that magnetic fields on the proto-neutron star have. I sort of couched that down here, but it could be more robust than we think. But then you have other sources that involve more extreme, rare channels of core collapse. So-called collapsars, magnetorotational instability, supernova, and magnetized proto-neutron star winds. I'll come to these in a second. These are not totally exclusive. It's quite possible that a MHD supernova precedes a collapsar, for example. And so the motivation here is that we have sort of these two classes of gamma ray bursts. We have the short ones and the long ones, which are separated by a few seconds. So the short ones, as I've mentioned, we think probably mostly come from neutron star mergers, and the long ones, although not all of them, it's clear now, but some of them are actually probably majority of them come from the collapse of massive rotating stars. And the evidence here is you see the GRB, and then after it, you literally see a supernova. So it's very compelling evidence. It took us a little bit longer to have this compelling evidence. And broadly speaking, the thought is that if these are both being fed by accreting black holes, the duration is essentially set by how long you're feeding it. So in a merger, you have a small accretion disk, you feed it for a short period of time. In a collapsar, you have to wait for the whole star to fall in, and that can take a few minutes or longer for the inner parts of the star. So this idea, of course, is you have this rotating star. If it fails to explode or otherwise forms a black hole, and if the star is rotating, then not all of the star falls into the black hole. You end up with this rotating disk of material, and some of it does make it into the black hole, but some of it can also be ejected in the accretion disk winds, which then could potentially be neutron-rich. So this has been, I should say that this is an old idea that collapsars could be some source of our process. I would say it was revived by Daniel Siegel et al. In our group in 2019, where we showed that it was possible that these disks do become neutron-rich, even if the star itself is not neutron-rich. I'll come to this in a second. So what I'm going to talk about is sort of some global simulations that were done by Dinat Isa, who's a graduate student at Northwestern, with Or Gottlieb and Sasha Tchaikovskoy. And so we were trying to see if it's possible in a 3D MHD context to get our process and ejection and production. And so it's using Hammer with M1 neutrino transport. And anyways, see if I play the simulation. What you're gonna be seeing with the colors is the electron fraction. So we're collapsing in here. We're forming a disk around the black hole. It becomes sort of moderately neutron-rich near the black hole, and we do get some of that neutron-rich matter out in the form of a jet for this particular simulation. I think the challenge of these is that you have to make the disk neutron-rich, and it needs to also be ejected from the disk and not just fall into the black hole. I personally think we see GRBs, so it's very clear to me that stuff is being ejected from near the black hole in reality, if not in our simulations. But if you have a very strong magnetic field, it becomes harder for these accretion disks to become neutron-rich. And just to remind you of the physics, it's very reminiscent of the post-merger disks. But the difference is, of course, the star itself is not neutron-rich to begin with, unlike a neutron star. A collapsing helium core is electron fraction of a half. But you can self-neutronize these accretion disks, provided that the accretion rate is above some critical value of typically a few thousandths or a few hundredths of a solar mass per second, which is readily achieved in gamma ray bursts. The issue is that if to get a jet out of this environment, we need a very strong magnetic field. The effective alpha of the disk, how dense the disk is getting, may not be as high as what you would guess for sort of a small value of alpha here. And so if you need a really high magnetic field to get the jet out, then maybe this ignition rate is higher than we originally thought, and maybe it's hard to simultaneously neutronize and eject material. But at least in this single case of a fairly high accretion rate system, Dennott found it was possible to eject our process material. And then this material, of course, goes out, will be a part of the supernova explosion. You can't really trust the electron fractions here because it's mixing with the rest of the star, and all the nucleosynthesis would have basically been frozen by this point. So, but you can nevertheless see that this low Y-ish material will mix outwards into the outer layers of the star potentially. And so this motivates a possible way to test this scenario by looking for imprints of the R process on sort of collapsar-like supernova. And the idea is, of course, that if we do produce these lanthanide and actinide elements, they have a much higher opacity than ordinary stellar material. And so if they were to mix out into the surface, it would substantially, sorry. Yeah. No, yeah, you could there. Yeah, thank you. So if it were to substantially mix out, you could appreciably redden some of the late phases of the supernova. Because in a supernova, of course, you see the outer layers first, and then you see deeper and deeper in. If you eventually reached a layer that was mixed with these elements, you could basically redden the supernova. This was an idea we studied with Jenny Barnes. And so, what we proposed as a search strategy was to follow up in the near infrared these collapsar supernova on timescales of sort of months. And if we saw some reddening or some deviation from what we see in other stripped envelope supernova, maybe that would trigger following up with JWST to see if there's any R process signatures. And there have been several groups that do this, but what I think people have realized is some of these do redden, but we don't know if it's dust or some other line effect. So it's actually hard just photometrically, I think, to test this scenario. So we need JWST to look at a collapsar supernova at late times. I believe there are some observations maybe coming out along those lines soon. We tried this. We had this event 211211A, which was a 34-second GRB. We thought, okay, and it's in our backyard. I forget the distance, 300 megaparsecs or something like that. And when the afterglow of the GRB faded, the weird thing was there was no supernova. We expected to see a supernova. It actually looked a lot like a kilonova, was sort of left over in the infrared when the afterglow faded. And with Jenny, we tried to fit the residual kilonova to one of these R process enriched collapsar models. And we found we could do it, but we needed somewhat weird parameters, like we needed the total ejecta mass less than a solar mass, very little nickel, and sizable amount of R process to produce the reddening. So you could argue, well, maybe Occam's razor is that this wasn't, in fact, a collapsar, a massive star explosion. Maybe it was a kilonova that just happened to have a 30-second GRB. And there's a lot of questions as to whether it's possible for a neutron star merger to produce such a long duration gamma ray burst. I think it is possible. I could talk about it, or Gottlieb has written, we've written some papers on this, but that may motivate, well, I'll come to this in a second. It may motivate thinking about other ideas. And then there was actually a second one of these long GRBs that had a kilonova. In this case, Andrew Levon got this nice JWST spectrum, which showed this sort of very red continuum and this potentially tellurium feature that was also seen in 170817. So suddenly we started seeing that a lot of long GRBs don't have supernova F them. They can have what appear to be kilonova. But then again, it's sort of this question, how do you make a long GRB from a merger? You expect the accretion disk to accrete within a few seconds. So how do I get 30 seconds of gamma ray burst emission? There's a few ideas. One of them is maybe the black hole is able to hold on to its magnetic field longer than it's accreting most of the mass. I encourage you to see this paper by Ora Gottlieb. But this has also motivated some more exotic scenarios, and one of them, which David and Patrick Chiang revived at Berkeley, is this idea of the accretion-induced collapse of a white dwarf. So here you have a white dwarf which is in a binary. Maybe it's sort of accreting from a non-degenerate companion, and it's an oxygen neon white dwarf. So when it reaches the Chandrasekhar mass, rather than exploding as a type 1a supernova, it undergoes accretion-induced collapse to form a neutron star. Now, if that white dwarf is also rapidly spinning, it's accreted angular momentum in addition to mass, so it's basically spinning at breakup. Then when it collapses to a neutron star, not all of it, again, will end up in the neutron star. Some of it will end up in a disk around the neutron star. And so you have a sort of an analogous scenario to a neutron star black hole merger, but replacing the central object with a neutron star instead of a black hole. And so with Luciano Combi, we did some 3D MHD, or he did some 3D MHD simulations of these accretion-induced collapse events, sort of witnessing the formation of the magnetized accretion disk around the white dwarf. I should say that this white dwarf cannot have a strong external magnetic field prior to its collapse, because it would then not be so rapidly spinning at the time of collapse. It would magnetically be breaking below that. So we had to put the magnetic field inside of the star, relatively weak magnetic field. But nevertheless, he found that you grow the MRI inside the star, the magnetic field does emerge from this accretion disk that forms around it. So you do create this sort of slowly rotating core, this sort of Keplerian disk that spreads outwards in time and creates these MRI stripes, which sort of drive these magnetic tower explosion. And it's fairly easy to explode these stars because they're such low mass. And so even within 150 milliseconds, it was clear we were sort of getting an MHD type explosion from these events, with substantial amounts of neutron-rich material coming out of the accretion disk. By the end of the simulation, we already had seen hundredths of a solar mass. If you sort of extrapolated it to the future evolution, you could easily get a few hundredths of a solar mass. And so this could mean that accretion-induced collapse could also produce a kilonova accompanying it. And of course, the big difference here is that at the end of the day, rather than having trapping everything in the spin of the black hole, you have a rapidly spinning, highly magnetized neutron star in the center. And if that neutron star, once the disk has evaporated, then goes on to undergo spin down, its outflow could provide a second source of prompt emission. And in fact, this was part of my PhD thesis. And when I was studying magnetars as a graduate student, their outflows and what types of internal shocks they would produce, at that time, we were seeing this extended X-ray emission after short gamma ray bursts, which we were trying to explain. And so I developed a model for what the magnetar wind would produce in terms of its internal shock emission. And it actually looks not terribly different to this extra component that we saw in 21A. So I don't know. Maybe we should be open that some of these mergers, some of these long GRBs with kilonova could be something completely different. And of course, if LIGO had been on, this event was at 300 megaparsecs, we might have been able to actually test this hypothesis, or at least come close to it. Okay, now I want to talk to you about something completely crazy. So about these collapsar disks. So if you have very massive collapsar disks, very high accretion rates, this may even require going to 100 solar mass above helium cores. The outer regions of these disks could become massive enough to actually get fragmentation, so gravitational instability. So you can get a tomb ray parameter, which is less than a few. And if you have gravitational instability and you have neutrino cooling, then that opens the possibility for fragmentation, much in the same way that you form, this is a formation channel for Jupiter, for example. And so if you sort of calculate what would be the Jeans mass inside these fragmenting collapsar disks, it's typically of order a fraction of a solar mass up to a solar mass. But crucially, because the disk is neutron-rich, unlike in an iron core collapse where the electron fraction is a half and the Chandrasekhar mass is 1.4 solar masses, you can't form subsolar objects. In these disks, the electron fraction is low, so the Chandrasekhar mass can be less than a solar mass. So in principle, you can fragment to form subsolar objects. And if these objects were then to meet each other in the disk, they might undergo mergers within the collapsar disk in a hierarchical fashion. And so you can get basically kilonova happening inside of this collapsar, maybe multiple ones, and then whatever is left over at the end of the day would eventually merge with the central black hole. This was actually first proposed by Tony Pirro and Eric Fall as an idea. And so with a student at Princeton, Yiqian Chen, we actually did some shearing box simulations of these collapsar disks with self-gravity neutrino cooling. We're doing the outer parts of the disk, so we don't have to necessarily worry about neutrino transport for the initial phases of the collapse. So we kept it simple, just optically thin cooling. We even did a very simplified assumed pair capture equilibrium. And anyways, this is the density, pressure, cooling time in dimensionless units and orbital periods. And not unexpectedly, if you have a sufficiently dense, massive disk, you can get fragmentation of these disks into a bunch of self-bound clumps. And in order to get this, you need very high, this should be m dot, very high accretion rates, and you need to be fairly far out on the disk. So that's have very large angular momentum disks. So at the end of the day, he found clumps with masses in this range and exceeding the local Chandrasekhar mass, and so that means that the clumps could continue to contract. Not even degeneracy pressure will halt their collapse, and they could form subsolar objects. Yeah, this is just showing the mass distribution of the clumps and showing that it's above their local Chandrasekhar mass. And so these are sort of forbidden neutron stars that shouldn't be formed in ordinary core collapse supernova. So we're finishing up our paper, and then LIGO announced this sub-threshold event S250818, which was only had a 30% chance of being astrophysical, 70% of just being detector noise. But they said with confidence that if it is a physical merger, one of the merging bodies had to be less than a solar mass. The chirp mass was down here. And so when ZTF followed this up in the spatially and temporally coincident with this event, there was a type 2b supernova they discovered in the air region. And a lot of the group said, oh, it's not a kilonova. This is not a physical association. But in fact, if these were subsolar objects formed in a collapsing star, the counterpart you'd expect to see it is a supernova, because all these mergers are happening, within in most hours, but probably minutes or so after the collapse. And so it's not the supernova I would have expected. I might have expected more of a GRB type supernova, but it is a stripped envelope supernova, which means there's a binary, which is the ingredient you need to spin up a star. So I'm not saying this is physical. I would not bet my house this is a real event, but I think it motivates us being open in the future to what kind of counterparts might accompany subsolar mergers if they exist. And then there was actually a few weeks ago a second event which had a higher false alarm or higher significance false alarm rate of 1 in 5 years. So it was a bona fide detection of another subsolar event. My understanding is that so far the observers have not found any counterparts to this event. Okay, so what is the census? So we have a few promising ideas. I think collapsar disks are promising. It may be hard to get the neutron-rich matter out generically. AIC, I think, is very promising as a form of magnetorotational supernova. I didn't talk about other magnetorotational supernova that happen in other stars. I think they're also promising. And the thing I want to emphasize is even if you have a magnetorotational supernova, what you formed probably is a magnetized protoneutron star. And so there's a subsequent proto-magnetar wind phase, which again has been studied recently by Dhruv and Tejas, and I think is very promising, and will also read my PhD thesis. But what I want to come to at the very end is, okay, after the dust is cleared, we have this magnetar left over. It will continue to be active for 10,000 years, and it may continue to be an interesting source of our process. And in fact, we may have evidence that magnetars can produce our process. And so just to remind you, magnetars are these very strongly magnetized neutron stars in our galaxy. They're actually formed fairly commonly. They emit flares over a range of energies, but their most powerful flares are giant flares, which release in just a fraction of a second, up to 10 to the 46 or 47 ergs of gamma rays. There have been 3 of these giant flares in our galaxy since we've had gamma ray satellites or in the LMC. The most powerful was SGR 180620, which took place in December 2004. And you can also see these outside of our galaxy more regularly. There was one just a few years ago in M82. They appear outside of our galaxy basically as short gamma ray bursts, but they're not from mergers. They're from these giant flares. And the analogy roughly you should have in mind is some kind of magnetic reconnection or eruption from the star that produces a pair fireball. And the magnetar is rotating. And so after the eruption of this fireball, it gets trapped in the magnetic field, and you see an oscillation as the star rotates, an evaporating fireball. There was already evidence back in 2004 that the giant flare ejected sizable baryonic mass into space. There was a radio afterglow that faded away after the event, which was actually observed with the VLBI directly, so you could actually see that it was expanding away from the magnetar at a fraction of the speed of light. If this was a pair ejection, it would be expanding likely much faster. The fact that it's subrelativistic strongly suggests there's a lot of baryons in it. And the modeling indicated that, maybe up to a millionth of a solar mass was ejected with a range of speeds between, say, 0.2 and 0.7 C. So there have been a few recent models for how baryons or crustal material is ejected during these giant flares. One idea we worked on with Jakub Sahula is that this dissipation of magnetic energy above the surface creates a high pressure region, this pair fireball, and that pair fireball drives a shock into the crust. And when the fireball leaves, the crust basically re-expands and a portion of the material is expelled into space. Recently, there's been another suggestion by Ashley Bransgrove and collaborators that these are more like magnetic bubbles that sort of emerge from inside the star. What I want to say after this is sort of independent of this. I think regardless of whether this is a hot or a cold, this scenario is more of a colder ejection. I think it's generic that you'll get nucleosynthesis in this ejected crustal material. My student Ani Patel did some Skynet simulations using Jakub's models for the thermodynamic history of this expanding material and found that it was possible to create our process elements at least up to, say, the first and second peak, possibly up even to the third peak if you have high enough entropies in this material. And much like in the case of kilonova ejecta, it undergoes this radioactive decay for a long period of time after you synthesize these elements. And so you get predict the analog of a kilonova, but associated with magnetar giant flares. But because there's a million, or not a million, but 10 to the 4 times less ejecta mass, rather than them lasting for days or weeks, they last for 10 minutes or something. So we called them nova brevis. But much of the physics is the same. The matter produces radioactive particles, the decaying matter, which are then thermalized by the ejecta and re-radiated in the UV optical infrared. And so we predicted that these would be fairly UV bright over the first 10 minutes or so. And so I think the way to discover these without having... So one thing is you could wait for the next one in the Milky Way, but we might be waiting a while since they only happen every few decades. Another thing is to go looking for them outside of our galaxy. In that case, you want to trigger on the gamma rays from the spike of and you want to point very quickly an ultraviolet telescope. And this is exactly what Ultrasat is slated to do for short GRBs. So I'm hopeful that Ultrasat could maybe detect these nova brevis from magnetar flares outside of our galaxy and confirm how much mass is ejected from them. But what we realized in the course of this calculation is that there also is you can also directly see the radioactive products. So this radioactive decay of these elements, part of the energy comes out, of course, in gamma rays as the nuclei de-excite. And these gamma rays are initially trapped in the ejecta, but they eventually can get out to some distant telescope. And so if you just say I have some expanding material, I have a certain optical depth through it for gamma rays, how long do I have to wait before the gamma rays can escape from the expanding material? For the typical values of ejecta mass and speed, this takes maybe 10 minutes for gamma rays to start to leak out. And so if you had one of these events in our galaxy, you could go looking directly for the gamma rays from the radioactive decay. And in the process of making this quote unquote prediction, we reached out to the observers who had worked on this event in 2004, and they basically said, oh, we already saw this in our data. There was an MEV afterglow following the 2004 flare, an extra component of gamma ray emission that started around 700 seconds after the event and then decayed away. And it was seen by three separate satellites, Integral, CONUS Wind, and RESI. And basically, no one had ever explained what it was. It was just called the MEV afterglow. And following the rise, it sort of decayed away as you'd expect for radioactive heating of the material. So Ani did a more detailed calculation given his models of these magnetar flare ejecta for what gamma ray emission would be produced, and this was sort of the gamma ray light curve. So he was able to the parameters of the model are how much mass you eject, what is the electron fraction below the surface of the crust that you're excavating, and at what speed you eject it. And so accounting for the fraction of the radioactive heating that is actually escaping following standard thermalization efficiencies, you're able to predict the gamma ray light curve and sort of match it to the data. And what he found is that you could produce the time scale, the peak flux, and the total fluence of the event, all if you assume that this event produced around 10 to the minus 6 solar masses. And so one could argue that this, was the very first kilonova that was actually, we had it already in our data, and we just didn't know we were seeing a kilonova back in 2004. And furthermore, if you then do the transport, so you're producing a bunch of MEV gamma ray lines, which are then Doppler broadened by the expanding material. And so you have to do the radiation transport through the expanding material. We've been doing this with Indrek Vroom, and what we find is we can actually also match quite nicely the spectrum that was reported by RESI. So we're able to produce also the spectrum within this single event. So just sort of, you might ask the question, okay, well, we have mergers. I said they could be a major source of our process. What about these giant flares? Well, these very energetic ones, like the 2004 event, it's thought that they only happen in the galaxy once every century or so. And we think that this event produced around 10 to the minus 6 solar masses. And so if you multiply these two numbers, the rate times the yield, you get their contribution to the R process in the galaxy. And then you have to account for the star formation history and other things, so it's a bit messy. But in the end, basically the galactic magnetar flares sort of sit here. If you say 100%, so this is the amount of our process per event, this is the rate. If you wanted to produce all of it, you need to be above this solid line. So the galactic magnetars are very low ejecta mass but high rate events. They probably only produce 1 to 10% of the R process. As we already said, mergers are high yield, low event rates, so they could be all everything we need. And then I've sort of put on a few other ideas here. If protoneutron star winds were our process sites, they might sit here. If collapsars occur, they might sit here. And then, of course, we also have FRBs, magnetars outside of our galaxy. They're even more energetic than FRBs. So I'm going to finish there and just say, I think we have a number of contenders for the origin of these heavy elements, some which both work theoretically and have been confirmed, like mergers. We have things that work theoretically but have not been confirmed, like black hole neutron star mergers. Of course, we need the black hole to be spinning. We have things that don't work and haven't been confirmed, like ordinary supernova. And then we have a bunch of stuff sort of in between. And I would say, where they seem to be promising, but we're sort of, have we seen AIC? Is that what these long GRBs with kilonova are, or something else? And then I think the other major take-home point I want you to make is that I think magnetar giant flares, I think we can understand theoretically why they work. If you eject crustal material from a neutron star, it's going to our process. And I think we have confirmation in the gamma ray signal we saw from the 2004 flare, but they're probably not the most dominant source in our galaxy. So anyways, I will finish there and take questions. Thank you.
Thank you very much, Brian, for a very nice talk and showing us different ways to create the heavy elements. Let me stop the recording.